So for today, I would like to talk about our experiment, and that is water amount per accuracy. So before we get into our experiment, I want to introduce you to the meaning of probability. So probability is the measure of how likely an event is to occur, expressed as a number between 0, impossible, and 1, certainty. So now I would like you guys to think of a situation where you have 2 guests inside of your home and you are serving them the same drink on the same shape of glass. And then you pour the drink into the first glass and you give it to the first guest. And then you pour the same amount to the second glass and then you give to the second guest. So now, do you think the amount of the drinks inside of the 2 glasses the same? Well, obviously it is not. So this is an example of random variation. So now, let us talk about our experiment. So the purpose of our experiment, water amount per accuracy, is to first record 30 readings of difference in water volume poured from the target measurement of 100 ml. Next is to calculate the mean and variance from the calculated data. And the third one, compare the observed variation to a suitable theoretical probability model based on a uniform distribution. So first, let us get into the records.
Here are the few tools and setup. First, we need to have 100 milliliters and 5 milliliters measuring cylinder, plastic cup, a cup of water, marker pen, notebook and pen to record data. Here are a few steps that we do in our experiment. First, use a measuring cylinder to pour exactly 100 milliliters of water into a plastic cup. Second, mark the water level on the plastic cup as the target line. And then empty a cup completely so it's ready for the first trial. Without using a measuring tools, pour water into the marked cup until it has reached the target line by sign only. And then use measuring cylinder to find the actual amount of water poured in milliliters. Subtract 100 milliliters from the actual volume to get the deviation. If the result is positive, so it's overfilled, and if it's negative, it's underfilled. Write down the deviation in milliliters for that trials in the data table. Lastly, repeat step 3 until 7 for the total 30 trials to collect enough data. The sample space is all possible value deviation values in millimeter that occur when pouring 100 milliliters of water by side. Deviation minimum equal to -7 and deviation maximum equal to 4.9. Sample size is between -7 and 4.9. For question 1, the variable measure is the deviation in millimeters between the actual amount of water poured, and the target is 100 milliliters. It is quantitative discrete variable since deviation can take any real values, positive, negative, or zero, depends on how much overfill and or underfill. For question 2, we are given sample of 30 observation of the different deviation. T usually means the difference between actual and target field. We want to find several probabilities based on how many times deviation is positive, negative, or zero. Deviation that less than and equal to 3 is equal to 21 over 30. So the answer is 0.7. Deviation that greater than 0 is equal to 10 over 30. So the answer is 0.333. And lastly, deviation is less than 0 is equal to 80 over 30. So the answer is 0.6.
So this is our result for the experiment. As you can see here, there are negative values and also positive values. Not to mention, we also have a result that is exactly 0. Moving on to the calculation of mean and variance. As you can see here, we have two different formulas to find the mean, but you can use both of them to find it. But the first one is A equal to 1 over n sigma with A sub I. A sub I is the total of our data. So by using this formula, you can simply sum up all the total data you have, and we got negative 31 over 31.9. When you divide it with the total trial, which is 30, you can get the mean. So the mean for this experiment is negative 1.0633. This shows that the result of the experiment is more likely to go around negative 1.0633. For the variance, we have the formula of S square equal to sum of total data minus with mean with square, and then we divide it with total data minus by 1. For this experiment, we can get the xi minus the mean with square equal to 276.5697. To find the variance, we can divide it with total of trial minus by 1, and we can get the variance, which is 9.5368 ml. By looking at the mean and the variance, we can see the mean is negative 1.06 ml. This shows that the participant tended to pour slightly less water than 100 ml target on average. This suggests a small underestimation when judging the water level by site. The standard deviation is about 3.09 ml, which indicate that the accuracy varies quite a lot. Next, we need to find the probability of D less than 0 and D greater than 0 and need to compare it. So as you can see here, the probability of D greater than 0 is 10 over 30, which is 1 over 3 and equals to 0.333, while the probability of D less than 0 is 18 over 30, which is 6 over 10, equals to 0.6. So the probability of D less than 0 is greater than probability of D greater than 0. This shows that the result is more likely to underfill than overfill.
So now, let's get into the discussion part. From the experiment, we can see a clear tendency to underfill the target amount. And we can see this from the mean itself. Now for question 5, we are asked the probability of D more than 0 given modulus D less than or equal to 5. So first of all, we need to find the number of trials for D more than 0, and that is 10. Then we need to find modulus D less than or equal to 5. Now, everything inside of the modulus, the answer will end up to be positive. Then we will have 28 number of trials for probability of modulus D less than or equal to 5. Now, let us answer the question. Probability of D more than 0 given modulus D less than or equal to 5 is equal to 10 over 28, and we will get 0.357. So now for question 6, we were asked whether underfill or overfill more often occurred in our experiment, and our answer is, of course, underfill. Underfill occur more often, with the number of underfill trials being 18 number and the number of overfill trials being 10. Now, let's get into the last purpose of this experiment, and that is to comparing experimental and theoretical probability. So since the data are approximately evenly distributed between negative 7 ml to 4.9 ml, we model them as a continuous uniform distribution. We use the formula of fx equals to 1 over a minus b, where a is the maximum value and b is the minimum value. So we just insert in the maximum and minimum value inside of the formula. So we will get 1 over 11.9 for negative 7 to 4.9. Now the experimental probability, probability of modulus d less than or equal to 5, is put 28 over the overall data, which is 30, and we will get 0.9333. Then the probability that the error is between 4.9 ml and 5 ml is 0, because from our experiment the maximum amount is 4.9 and 5 ml is out of our experiment data. So when it is out of our data, obviously it is elsewhere, and when it is elsewhere, it will be 0. Now the probability of error is less than 5 ml. Probability d modulus less than or equal to 5 is also equal to probability of negative 5 less than or equal to d less than or equal to 5. And then we just integrate it from negative 5 to 4.9 plus from 4.9 to 5. So we already get the answer of from 4.9 to 5 is 0. So then we integrate as usual, and we will get 9.9 over 11.9, which is equivalent to 0.8319. Now let's compare experimental versus theoretical. Experimental versus theoretical. So from our calculation just now, we do know that the experimental probability, which is 0.933, is higher than the theoretical probability, which is 0.8319. This might be caused by small sample size because we only have 30 trials. Next, it might be human errors, and for this for our experiment, one of the human errors might be the eye level error, and the third one might be because of the rounding error.
Question for chapter 3. First, fx equal to k 1 minus modulus x. X is between negative 1 and 1. So we get k is equal to 1. Fx 0 x is less than negative 1. X plus x squared over 2 plus 1 over 2. X is between negative 1 and 0. 1 over 2 plus x minus x squared over 2. X is between 0 and 1. And lastly, 1 x greater than 1. For question 2, Ex equal to 0. So Ex squared is equal to 1 over 6. So lastly we get var x equal to 1 over 6. Now I will explain how I calculate the moment generation function or MGF for the variable x. We start with the formula of the MGF, which is mx of t equals e of e to the power of tx. Since the probability density function is symmetric, instead of integrating from negative 1 to 1, we can simplify the work by integrating from 0 to 1 and multiplying the whole thing by 2. So the MGF becomes 2k times the integral from 0 to 1 of e to the tx multiplied by 1 minus x. To solve this, I split the integral into two parts. For the first part is the integral of e to the tx, and the second part is the integral of x times e to the tx. Splitting it like this makes the calculation easier. For the first integral, the result is straightforward. The integral of e to the tx from 0 to 1 gives us e to the t minus 1 divided by t. Next, for the second integrals, which is x times e to the tx, we need to use integral by parts. Here I choose u equal x and dv equal to e to the tx dx. Then du equals dx and v equal e to the tx divided by t. Applying the integral by part formula and substituting the limit from 0 to 1 gives us an expression involving e to the t and t square. Once we have both integrals, we substitute them back into the main formula and simplify. After simplifying all the terms, we get the final expression for the moment generation function. For the moment t is equal to 2 negative 1 over t plus e to the power of t minus 1 over t square. So, moment of 0 is equal to 1.
As for the conclusion for the experiment is, the experiment shows that human Turing accuracy can be effectively analyzed using probability. The experiment shows that human Turing accuracy can be effectively analyzed during the experiment of the probability. The deviation recorded demonstrated that natural variation caused by small judgment errors when estimating 100 ml mark. The distribution of the data clearly reflects that this variation, with most values falling within a consistent range of underfilling and overfilling. This experimental mean is slightly negative, indicating a small but consistent bias toward underfilling. This aligns with the observed probabilities where underfill occurred more frequently than overfilled. The close relationship between the overall pattern of the data and the expected behavior of random measurement error shows that the probability is a useful tool for modeling real-world human variability. Key learning: always base the probability analysis on actual experimental variations, including the frequency of overfill and underfill, using the full set of raw data to compute the mean, variance, and empirical probabilities. Provides the most accurate representation of real measurement behavior. That's all from me.